Next, go for the numericals. What is the next question? It says that the two identical charges capital Q each are placed at a distance of r from each other. A third charge small q is placed on the line joining the above two charges such that all the three charges are in equilibrium. This is our key point over here. Three charges have to be in equilibrium. So what will be the magnitude, sign and position of the charge small q? So first of all, we will depict the given situation in the form of a figure. We have to place the two identical charges capital Q and capital Q at the points A and C respectively, separated by a distance of r. Now where the third charge small q must be placed, the small q must be placed in between the line joining the two charges. Then only the system of all the three charges will be in equilibrium. If you place them either to the right side or to the left side, all the three charges will never be in equilibrium. So in order to satisfy the given condition, if q is placed at a distance of x from A and B, then what condition we will be having? The charge will be, the small q will be in equilibrium if the forces exerted on it by the charges at A and C must be equal and opposite. Now when q is placed at a point B, now the charge which is at A and the charge which is at C, they will exert equal and opposite force on the charge small q. Then only the small q charge will be under the equilibrium condition. On putting the magnitude part in the formula, what we will get, this is the force between the charges at the point A and B, and this is the force which is present between the charges at point B and C. This is B and C. They are separated at a distance of r minus of x. Why? Because the total distances are, out of which the distance between A and B is x. So what will be the remaining distance? The remaining distance B and C will become r minus of x. So this is the two forces that are present on a small q charge because of the charge at A, and this is because of the charge at C. On cancelling the like terms, what we will get? On this term, and on solving the term, we will get the position of a small q must be at r by 2. That is, the small q must be placed at the center of the line joining the two charges. Now the key point must be in order to find the sign of a small q. Now how we can find the sign of a small q? The sign of a small q we can get by considering a concept that if capital Q is to be in equilibrium condition, if capital Q is in equilibrium condition, that means the two forces which are present on capital Q must cancel each other. Now what is the force which is acting on the charge which is present at A? The C charge will be repelling this charge in this direction. The charge at C will be repelling the charge at A in this direction. So the charge at B, which is a small q, must attract the charge at A, so that the charge at A will become in equilibrium condition. So the charge at A is under the two forces. One is the attractive force by the small q, and one is the repulsive force exerted by capital Q. This is the key point. This is the key point or the deciding factor which will decide what should be the sign of small q. So the sign of small q has to be opposite to that of the capital Q. Then only the system of all the three charges will be in equilibrium. If you will take the sign of small q as same to that of capital Q, then the three charges will never be in equilibrium. Keep this key point in mind, that if the system of three charges are in equilibrium, the third charge has to be in opposite in nature. So now after that, our given condition will be force of repulsion between A and C must be equal to the force of attraction between A and B. So the repulsive force between A and C, that is repulsive force between capital Q, and the force of attraction by the small q must be same. That is, on putting the magnitude form, we can get this cancels out. So what we are left with, Q equals to Q by 4. So this is the magnitude part. What is the sign of the small q? Sign of this is just opposite here. Mind it, here we are not mentioning the sign of Q is positive or the sign of Q is negative. We are not mentioning any of the sign. We are just mentioning whatever be the supposed sign of the capital Q, the opposite sign must be carried by the small q. That should be your answer, not in a way that it should be positive or negative. This is the key point where you have to give the stress. The sign must be opposite to that of capital Q. Now next question, let's say another question which is again based on the condition of equilibrium. Now 2 point charges of charge values capital Q and small q are placed at a distances of x and x by 2 respectively from a third charge of value 4q. All charges being in the same straight line. Now calculate the magnitude nature of capital Q charge such that the net force experienced by the charge Q is 0. Here we have to take the two conditions. One is of capital Q charge and the other one is of the small q charge. Keep this in mind. In the previous question, we were having the equilibrium condition when all the three charges were in equilibrium. Here only small q charge is in equilibrium. So let us see first of all how the three charges can be placed. The three charges we are placing according to the figure here. From a charge 4q which is placed at A, the capital charge q which is placed at B is at a distance of x, and the another charge small q which is placed at a distance of C at a distance of x by 2 from 4q. Now what will be the key point over here in solving the question? For the equilibrium of the charge small q. Now according to our question, small q charge is at equilibrium. Under which condition it will be equilibrium? When it is under the experience of two equal and opposite forces. Now C will experience a force from A and C will experience a force from B, and these two forces must be equal and opposite, that is FA and FB must be equal and opposite. So what we can depict is that the charge on capital Q must be same as that on the charge of 4Q. Then only the C will be under the action of two equal and opposite forces. So what will be the sign of capital Q? The sign of capital Q must be the same. Here again we are not mentioning that the sign should be the positive or sign should be the negative. Here we are just mentioning the sign of capital Q which is at B must be similar to the sign of 4Q which is placed at A. So this one will be your key point. It is not opposite, otherwise the charge at C will not be in equilibrium. Now again, so according to our this key point condition, FA must be equals to FB. Now we have to put the Coulomb's law. What is that? X by 2 and X by 2. We have to put the formulas over here. So both of them are at a distances of X by 2 and X by 2. So like terms get cancelled out and we will get the magnitude of capital Q as equals to 4Q. Consider three charges Q1, Q2, Q3 each equal to Q at the vertices of an equilateral triangle of side L. What is the force on a charge capital Q with the same sign as small q placed at the centroid of the triangle? So for this question, let us try to understand what the figure is, what the figure can be. So first of all, we are having an equilateral triangle. So suppose A, B, C, it is an equilateral triangle of side L, L and L. Next, the Q1, Q2 and Q3. So Q1, Q2 and Q3, they each are equal to Q, Q and Q. They are placed at the vertices of A, B and C with the position vector that is now O is the centroid. At the centroid, what we are placing, we have placed a capital charge Q. So suppose at the centroid capital Q is placed with the same sign as that of the small q and small q. So what will be that? We want to compute the force on capital Q. So for that we should know the distance between AO, the distance between BO and distance between CO. So AO distance will be equals to, let us suppose R. Similarly BO distance will be in this direction, it will be also equals to R. Similarly, CO, which is in this direction, it is also equals to R. So we have got all the distances. Now let us calculate the force on charge capital Q due to Q1. So now Q1, which is placed at the point A, it will be exerting a force of F1 which is in the direction of AO. So its magnitude we can find with the help of Coulomb's law, which will be 1 upon 4 pi epsilon naught Q1 upon AO square, where AO square is the distance between the 2 point charges. Here we have taken in general notation. After that we will put their respective values, and it is and in this AO is the unit vector pointing from A to O. Similarly, if we will find the force on charge capital Q due to Q2. Now where Q2? Q2 is at the point B. Now this Q2 will exert a force F2 which will be in this direction, and its formula we can have 1 upon 4 pi epsilon naught Q2 upon BO square, because the distance between Q2 and capital Q is BO and its unit vector will be along BO. Similarly, what is the third charge we are left with? So it will exert, that is this charge at C, that is Q3, will exert a force of F3 in this direction, whose magnitude will be 1 upon 4 pi epsilon naught Q3 upon CO square, which is in the direction of CO, and unit position vector will be CO. So there we have got the formula according to Coulomb's law. Now on applying the principle of superposition, what I have said it earlier is that total force on this capital Q charge, which will be F. So what will be the formula? It will be the vector sum of F1 plus F2 plus F3. Now let us see what will be the vector sum. So we have to add all the formulas, that is F1 plus F2 plus F3. If we go for their magnitude wise, they are all equal, that is capital Q into Q. Why? Because Q1, Q2 and Q3, they all are equal to Q. So for that we can place them as Q. Upon 4 pi epsilon naught. What is AO, BO and CO? AO, BO and CO, already we have assumed that their distance are same, that is equals to R square. So now here we have put the values of Q1, Q2, Q3 and that is AO, BO and CO. After that, here vectorially we have to add. So the unit vector AO, unit vector, unit position vector BO, and unit position vector CO, they are being added. Now next, what concept we are having? Angle between each pair of unit vectors AO, BO, CO. That is, AO is in this direction, BO is in this direction, and CO is in this direction. The angle between them is 120 degree, and they all form a triangle of cyclic vectors. About this concept you would have learnt in 11th class. So the triangle of a cyclic vectors always add up to 0. So what conclusion we are getting? The unit vector, the sum of unit vectors AO, BO and CO will be equals to 0. So this particular term in our equation, it will become equals to 0. So net force will become equals to 0. So this one will be our answer. The net force on capital Q charge which is placed at the centroid of an equilateral triangle, it will be equals to 0. So please go for all the steps I have given in a very nice way, so you may be able to understand it very clearly, and if you will write all these steps, there are no chances of losing any marks. Next, go for the second question. Consider the charges Q, Q and minus Q placed at the vertices of an equilateral triangle as shown in the figure. What is the force on each charge? So let us see what the figure has to say. So here we are having Q, Q, Q. That means they are equilateral triangle. We are having A, B and C. So is Q, let us for simplicity we have taken Q1 is the charge, Q2 is the charge having the magnitude positive Q and positive Q, and Q3 which is placed at point C, it is having a magnitude of minus 2. They are placed at the vertices. Now equilateral triangle, that means the side of the equilateral triangle is L, L and L. Next, the forces of attraction or repulsion. Now let us see whatever is the force acting on the point charge placed at A. Now the force which is acting on the point charge A, it will be under the repulsive force due to the charge at B. That means because they are of the same sign. You will find Q1 and Q2, they are of the same sign. So this Q2 will exert a force in this direction which is of magnitude F. Similarly, now Q3 which is placed at C, its magnitude according to our question is minus Q. So this negative charge Q3 will attract the charge at A, that is Q1, in this direction. So this will be the force on A due to the negative charge. So if we want to compute the force on Q1, its net force will become F1 and their magnitude will be the FF magnitude. That is, it is acting at a distance of L whose point charges are Q and Q. So what will be the magnitude? It will become 1 upon 4 pi epsilon naught Q square by L square. The point charge at A is under the force of attraction due to Q3, and it is under the action of repulsion due to the charge at B, but whose magnitude will be 1 upon 4 pi epsilon naught Q square by L square, because the separation between these charges are L and L. Similarly, if we want to find the force acting on B, so the B will be under the repulsion force of due to A, which is in this direction, and the attractive force F will be acting in this direction, whose magnitude will be the same one. Similarly, if we want to compute the force on charge C, which is Q3, that is negative. Now, negative charge will be attracted by the charge at A and it will be attracted by the charge at B because they both are positive. But magnitude will be the same, which is F, because they are separated at a distance of L and their magnitudes are Q and Q. So, again the formula will be, so this is force of attraction and repulsion. Whether we are having attraction or repulsion, the magnitude will be the 1 upon 4 pi epsilon naught Q square by L square. So this is the general computed formula we have just derived. Now we will go for the vector addition. Now by parallelogram law, net force on Q1. Now we want to find the net force on Q1, which is F1. Now this F1 will be the vector sum of this F and this F. Two F's that are acting and their angle between them, because they are exterior angle to the equilateral triangle, so it will be 120 degree. So vector addition if we will apply, so what will be the magnitude? Under root of FF is F square plus F square plus twice of FF cos 120 degree, and its direction will be pointing along BC. Mind it, here they are pointing in this direction, which is the direction of BC. On solving this, putting the value of cos 120 degree as minus 1 by 2, what we will be having is that under root of, we will be having 2f square minus of f square. We will be left with this term. So it becomes simply the under root of f square. On removing the under root, we will get f and simply f, and the direction will be along BC. This is acting along the BC side of a equilateral triangle. So this is the magnitude as well as the direction, the force acting on the F1, that is Q1 charge. Similarly, by parallelogram law, net force on Q2. Now let us see what is the net force on Q2. So the net force on Q2 we are finding it is under the action of one this repulsive force and another one is the attractive force whose magnitude already we have given. So again by applying the same parallelogram law by this vector addition, the magnitude, the angle between these two forces is again 120 degree. So again we are going to get by solving the same step, we will get the formula for F2 as F, but the direction this time will be along the AC side of this. See, this is the direction of F2 which is along the direction of AC of the equilateral triangle. Next we want to find the force on Q3. So net force on Q3. Now Q3 it is under the action of two attractive forces F and F. They are acting at an angle of 60 degrees. So here we will again apply the vector law of addition. This time F3 will be under root of F square plus twice of FF. This is cos 60 degree. Now by putting the value of cos 60 degree and solving this equation, we will get the answer as root 3f and it will be pointing in this direction, which is suppose unit vector, normal vector, and its direction we have to mention. So this is how we have calculated the force on each charge. So what are they? F1 will be F in the direction of BC. F2 will be again equals to F whose magnitude it will be this much. You can put the magnitude this much, but direction you have to mention it is along AC. Similarly, for the force on F3, that is F3 force, it will be the root 3 times of this magnitude. So mind it, here for F you have to put this value 1 upon 4 pi epsilon naught Q square by L square, and its direction will be unit vector, normal vector, which is pointing in this direction. With this we have solved this question. I hope you would have understood and go for all the steps. Let us go for our next question. The next question says that 4 equal point charges, each 16 microcoulomb, are placed on the 4 corners of a square. Now this time this is a question based on a square. Earlier we were having for the equilateral. For the 4 corners of a square of side 0.2 meter, calculate force on any one of the charges. So let us depict this particular figure. How we can say, let us suppose we take a square ABCD and calculate the force on any point charge, suppose which is Q4. So let us take the how to see the figure A, B, C and D. This is a square on which we have placed a charge Q1, Q2, Q3 and Q4, each of magnitude 16 microcoulomb. Now the side of the square is 0.2 meter and everywhere we are having 0.2 meter. Now if we want to calculate the charge on Q4, now the Q1 will be exerting a force on Q4 in the direction of, that is AD, which is called as the F1 force. So first of all we will calculate the magnitude of the force exerted on Q4 by Q1. How to find this magnitude? We can find this magnitude by the help of Coulomb's law, which says that 1 upon 4 pi epsilon naught Q1 Q2 by R square. Now this is the standard formula. Throughout our video I have been referring to this particular formula. So this time I am directly putting the values. So what we are having, 1 upon 4 pi epsilon naught is 9 into 10 to the power 9. Q1, Q2. Here we are having Q1 and Q4. That means the two charges whose magnitude is 16 into 10 to the power minus 6 coulomb. Here we have converted the 16 microcoulomb to the SI unit. So we have to put 16 into 10 to the power minus 6 and again 16 into 10 to the power minus 6 upon R square. So what is R square? R square is the distance between the 2 point charges. So here the distance will be the between A and B, which is 0.2. So we have to do the 0.2 ka whole square. On solving this part, we will get the value 57.6 Newton and it's in the direction along AD. So we have to mention the direction as well. Next we will calculate the force exerted on Q4 by Q2. Now where we have placed Q2, Q2 is placed on the point B. Now what will be the formula? The formula again will be based on Coulomb's law. So here 1 upon 4 pi epsilon naught we will put as 9 into 10 to the power 9. Q1, Q2, that means the value of Q2 and Q4 we have to put, that is 16 into 10 to the power minus 6 and 16 into 10 to the power minus 6 again upon R square. Now this time how to calculate this distance between the two charges, that is BD. Now we know that this BD is the hypotenuse side of a right angle triangle BDC. So this side BD will be equals to the, we know by using the hypotenuse theorem, it will be equals to the 0.2 whole square plus 0.2 whole square. That will be the under root of, using the Pythagoras theorem, by using the square of BC square, under root of BC square plus DC square. So we will put the magnitude 0.2 square plus 0.2 square. So this value we have put, and if we will do the square of this distance, we will remove the square root. So we will get 0.2 square plus 0.2 square. On solving this magnitude part, we will get the value as 28.8 Newton. Now the direction of this F2 will be along BD. So here we have to mention that its direction is along BD. So now I think F1 this direction and F2 these two forces will be clear to you. Next, we will calculate the force exerted on Q4 by Q3. Now, where we have placed Q3? Q3 is placed at the point C. So, again by using the Coulomb's law formula, what we can have, that is Q1 Q2 by R square. So, 9 into 10 to the power 9 we have to put, Q1 Q2 the same magnitude to put, and the distance between D and C is again 0.2 ka whole square. So, we will solve this part and we will get 57.6, the same value as F1, and this F3 will be pointing along the CD direction. So, here F1 and F3, they are equal in magnitude, but their directions are perpendicular to each other, that is F1 and F3 are perpendicular. So, what will be the resultant? So, mind it here, the resultant will be along this particular, between the F1 and F3. How to get the magnitude part? Under root of F1 square plus F3 square, that we all know how to get the resultant of two perpendicular vectors. So, by putting the magnitudes of 57.6 whole square plus 57.6 whole square, we will get the value as 81.5 Newton, whose direction will be along BD. Now, mind it, here the direction will be along B to D. Now, along B to D, already one force F2 is already present, and now another force will be superimposed on F2, which is the resultant of F1 and F3, that is this F dash force will be superimposed on F2, then only we will get the net force on Q4. That means, what will be our next step? Total force on Q4. Now, this will be the final part of our answer. So, total force is F. How we can get? It is simply by the algebraic addition of F2 plus F dash, because both the two forces are acting along the BD direction. F dash as well as this F2 is also acting along the BD direction. So, we have to simply add, that is this magnitude 28.8 Newton and this 81.5 Newton we have to add, and by adding we will get this value, and the net direction is along BD. I hope with this particular equation question, the concept of superposition of principle might get clear to you.